In this paper, we present PADL, a framework for training language-directed controllers for physics-based character animation. Reinforcement learning has been an effective paradigm for training simulated characters to perform complex and lifelike behaviors. These models can produce high-quality motions, but they generally only provide a restrictive interface for controlling a character's behaviors at runtime. In this work, we aim to develop a more expressive and versatile control interface by leveraging natural language. Our system decomposes a character's behaviors into tasks and skills. The task represents high-level objectives that the agent should accomplish, such as moving to a target location. The skill represents low-level behaviors that the character should use to accomplish the desired task. For example, in order to move to a target location, the character can walk or run to the target. Our system allows users to specify the desired task and skill using language commands. Our framework consists of 3 stages. First, in the skill embedding stage, we learn a shared embedding space for text and motions using a dataset of motion clips and captions. Next, in the policy training stage, a collection of reinforcement learning policies are trained using this skill embedding, where each policy is trained to perform a particular task while imitating skills from the motion dataset. Finally, we aggregate multiple policies together to create a multitask controller that can be directed to perform a variety of tasks and skills. Given a dataset of motion clips and captions describing the behavior depicted in each clip, we train a shared embedding space that aligns motions and text. This is done by training a motion encoder and a language encoder to map a motion clip and its caption to similar points in a shared embedding space. A motion decoder is also trained to reconstruct the original motion clip from the embedding. Once an embedding has been learned, it is used to train control policies that can be directed to perform different skills using natural language commands. Given a motion clip, the motion encoder is used to map the motion into a latent variable. The policy is then conditioned on the latent and trained to imitate the motion clip corresponding to the latent using adversarial imitation learning. This policy can then be directed to perform different skills using natural language commands. Our model is robust to new commands that were not observed in the dataset. In addition to imitating motion clips, the policies can also be trained to perform different high-level tasks. Separate policies are trained for each task. For this facing task, the character is trained to face a target direction while performing different skills specified through a language command. Next, we train a control policy for navigating to a target location. Language commands can be used to direct the policy to use different locomotion skills to move to the target. The character can also be trained to knock over a target object. Once a collection of single-task policies has been trained to perform different tasks, the policies can be combined together to create a single multitask controller capable of performing a variety of tasks and skills. For the multitask controller, we use the task command to identify the relevant task and the target object. The task and object selection is performed through a multi-choice question-answering framework using a pre-trained BERT model that has been fine-tuned on the SWAG multiple-choice dataset. The multitask controller can then be used to direct a character to interact with different objects in the environment using various skills. The character can be told to move close to a particular object. It can be directed to face a specific object while performing a particular skill, as well as to knock over a target object. As the user's task command changes, the multitask controller dynamically activates different single-task policies depending on the desired task. The learned skill embedding automatically leads to semantically salient interpolations between different skills. When interpolating between a walking and running skill, the policy learns to smoothly increase its speed, even though the intermediate behaviors may not be present in the dataset. Using an adaptive schedule for adjusting the weight of the task reward is crucial for training effective policies. If the task weight is too low, the character ignores the task and simply imitates the motion clips. If the task weight is too high, the character can develop unnatural behaviors. Our adaptive schedule is able to better balance the different objectives. Multitask reinforcement learning is known to be a challenging problem. In our experiments, training a single policy to perform all tasks leads to poor performance. Aggregating multiple single-task policies leads to much higher quality results. Paraphrasing some commands can still sometimes lead to incorrect behaviors. Not all skills are compatible with a particular task. Directing the character to use an incompatible skill to perform a certain task can lead to unnatural behaviors. Similarly, directing the character to perform a skill that is very different from what is in the dataset can also lead to unintuitive behaviors. More details are available in the paper. Thank you for watching.